Good morning, good afternoon, or good evening. This is now question 5 of the Step 3 2024 paper. As with all of these questions, hopefully you've had a go at the question yourself first, and you've even been successful, and now you're just looking for some hints and tips or other ways to think through the problem, or you're looking for a hint. And hopefully this video will give you such. As a reminder, you should only be tackling this after you've had a good go. Otherwise, you will be losing almost all the value from tackling the problem yourself. And let's get started. So this question 5, is talking about matrices. We're talking about non-singular, so a determinant is non-zero, and they're 2 by 2, and we've defined the trace. The trace is the sum of that main diagonal. So first up, we're going to prove a couple of results. Prove that for two matrices, M and N, the trace of the product is the same either way round. Okay, well, best way, let's give M and N some names. So M is going to be A, B, C, D, and N, could choose small letters E, F, G, H. Seems to work quite fine. It's half considering using some Greek letters there, alpha, beta, gamma, delta, but normal characters seem to work fine. So we want the trace of MN and NM. So let's work out what both of those are. So MN, this is going to be algebraically really unpleasant. So that's A plus BG for that. AF plus BH. CE plus DG. And finally, CF plus DH. So the trace of MN is going to be the diagonal AE, BG, CF, and DH. Now let's hope when I multiply the other way round, it's going to give the same diagonal elements, maybe in a different combination is what I'm expecting. So this time it's going to be AE plus CF. Again, I'm just looking that times that. So then it's going to be BE plus that times that, yeah, plus DF, and then AG plus CH, and finally BG plus DH. So the trace of NM is AE, CF, BH, DH, and we can see that these are identical, but the BH term and the CF term came from different places. So therefore, the trace of MN is the same as the trace of NM. Okay, and derive an expression for the trace of M plus N. Well, M plus N as a matrix, we just add component-wise. So is as so. So therefore, apologies. Therefore, trace of M plus N is AE plus A plus E plus D plus H, but A plus D was the trace of M, and E plus H was the trace of N. Okay, so part I feels like it's a setup part of the question. We'll likely use these two results slightly later on. Keep an eye out for where this trace might be useful. Carrying on though, we have the entries in a matrix are functions of t. The derivative of the matrix denotes the matrix whose entries are the derivatives of the corresponding entries. So as you would expect, if you differentiate a matrix, you're going to differentiate each term separately. Okay, so now we want to show something, some kind of matrix differential equation. 1 over det m is equal to that stuff. Now we could try and use one of the results from above. We have here a product of two matrices, so we can reorder them, but reordering them using that condition up there really isn't going to be helpful. This does look quite unpleasant because the m inverse times the derivative of m is going to be quite unpleasant, but we might as well try and see how these break down. So I'm going to set up, I'm going to try and show that left-hand side is equal to the right-hand side. So I've got the left-hand side to start with as 1 over the determinant times the derivative of the determinant of m. So that's going to be 1 over AD minus BC using the same m that's been defined above. And then we've got the derivative of the determinant of m, which is again AD minus BC, but all of A, D, B, and C are functions of t. So if I'm wanting to differentiate that, I'm going to have to product all various parts. So it's going to be AD dash plus A dash D minus BC dash minus B dash C. Is there anything clever I can do with that? Maybe. I'm also looking at what I want the answer to be. I want the answer to be equal to the trace of a product. So it should end up looking like something like this with the correct terms in the correct places. And it kind of does. If you take the D dash is the E, the A dash looks like it could be the G, maybe. But there are some sign differences. So I'm going to do what's sensible and also look at the right hand side. So this was the left hand side. So I'm also going to look what the right hand side does. The right hand side is the trace of m inverse. Well, m inverse is 1 over det m. Well, that's where this 1 over det m is coming from. The inverse of the matrix is dA negative B negative C. Yep. I always have to do a double little check, expanding out one of the components to check I've got the swap and the negative sign in the right places, times by the derivative of the matrix M, which is A dash B dash C dash D dash. One thing you can say about the trace is it is what we'd say is linear. So any multiplying factor we can kind of factorize out. If you times every component of a matrix by the same value, then you certainly times the sum of the diagonal elements by the same value. Multiplying that matrix out, we're going to have A dash D minus BC dash in the top corner, B dash D minus BD dash, minus A dash C plus AC dash, and minus B dash C plus A D dash. I paused slightly there because I was slightly worried that this term and this term were the same, but the derivatives are on separate components, so that's all fine. So then the trace is then going to be 1 over the determinant, and then add together the diagonal elements, minus B dash C plus AD dash, which is exactly what we had in the line above. If you do check, these two are identical. So this thing is indeed equal to 1 over det m times the derivative of det m. That seems like quite a shocking result, that the trace of with an inverse matrix involved is really just the derivative of determinants. Odd. I certainly haven't seen that kind of result before. Part 3. This part, matrix M satisfies the differential equation. where the entries are also functions of t. Show that those are all independent of t. Okay, so we would like to show basically that the derivative of det m is 0. That'll mean you're independent of the variable. You're a constant with respect to that variable. Similarly for the other two things there. So if I want to differentiate det m, well, let's use the result above. So the derivative of det m by part 2 is det m times by the trace of m inverse times the derivative of m. But we know the derivative of m is given by that formula, and I'm pre-multiplying by m inverse. So this is the trace of n minus m inverse n m. Well, I'm aiming for this thing to be 0, so let's hope some nice things happen. Now let's use some of the results from part I. The second result was if I added traces. If I did the trace of a sum, that's the sum of the traces. So I can write this as the trace of n minus, I'm adding a negative matrix, the trace of m inverse nm. But let's use the other result from part I, which said that we can reorder the matrices. So I'm going to put this whole section here behind that m. I'm going to treat that m inverse n as one matrix. So m's at the front, then m inverse, then n. But those is just the identity matrix. So this is det m times the trace of n minus the trace of n, which is beautifully 0, which then implies exactly what we wanted, that det m is independent of t. Nice. Now, can we do the same thing for the other things? We want the trace of m. Well, that's not as obvious. We want to differentiate the trace of m. Well, I could take, if I take traces of that equation immediately, if I take traces of this, then the trace of that is equal to the trace of that. But we can show, so one thing that's really good, so let's notice that the derivative of the trace, well, if m is the normal matrix, the trace is just a plus d, so the derivative is a dash plus d dash, which is exactly the trace of the derivative. Okay, but the trace of the derivative is the trace of mn minus nm, because that's what the derivative of m is, which is the trace of mn minus the trace of nm, which equals 0 by the same results that we've just used. Thus, trace of m is independent of t. So that's the second one done. Now we want to try and differentiate the trace of m squared. Now, we could try and set up another result. We could actually multiply out m squared and see what that gives us. If I do imagine that slightly, well, let's again do the same thing. Let's notice that m squared is not going to be pleasant. It's a squared plus bc. And really, I only care about the trace of this. AB plus BD. And I would heavily recommend that you do such multiplications out a little bit slower to avoid any errors. This is quite easily I get some algebra here wrong, but I trust that. So the trace of m squared is a squared plus 2bc plus d squared. Do I want to differentiate that? Because I would quite like to show this is independent of t. I suppose I should. So let's do d by dt of this thing. The issue now is we both have kind of product rule, kind of implicit differentiation going on. So this one's going to be 2a dash plus 2bc dash plus 2b dash c plus 2d dash. Now, how do I deal with that? How is that going to be something useful linked to some of my other statements? I can certainly factor the 2 out, because I'm aiming for this to be equal to 0, then that 2 really is doing nothing. Can I write this as the trace of something else? Because I can kind of I'm kind of imagining a matrix which has diagonal elements as so. But then if I do that, it's not going to help me particularly much, because I'm then going to be saying the trace of something like that. And why would that be equal to 0, even if I can factor it into 2? Now, factorizing a matrix just seems ridiculous. You never really want to undo matrix multiplication. So is there another way to think about the trace of m squared? Well, the thing above isn't going to really help. The fact that the trace of mn equals nm, that's the trace of mm trivially equals trace of mm. It's not an addition. Can I use the differential equation that we set up in part 2 to force an m squared? Can this thing here look like m squared? Well, that looked like it could have been a sensible factorization. So we kind of have something that looks similar up here, but the a's and d's are in the wrong places. So that's not going to work particularly well. So how do I think about this? Unless this thing is... Oh, that would be convenient. I'm now thinking, what is m times the derivative of m? And if I think about, this matrix briefly, and maybe this trace is exactly the trace I need, and lots of nice things happen. So if I do multiply this out, I get a dash a, b c dash, and in the bottom corner, I'm getting b dash c plus d dash, which is exactly what it is. So this thing is 2 lots of the trace of m dm by dt. Why is that useful? If I differentiate That's actually quite a, just noticed that if we kind of think of this as a as its own variable and we apply the chain rule to it, an implicit differentiation, we bring down the 2, the m squared becomes an m, and the chain rule says times by a dm by dt. So somehow magically our rules of algebra have also applied to rules of matrices, which is nonsense. But why does that help? I can put dm, I can put dm by dt in. So this is going to be 2 lots of the trace of m n minus m n m, and I've purposely not put these m's together because I want to do the same trick that I've done a few times, and that's reordering a multiplication inside the trace. So this is 2 lots of the trace of mmn minus the 2 lots of the trace of mmn, which does indeed equal 0. Thus, the trace of m squared is independent of t. Hey, a fascinating few results there, that just from this differential equation, which is quite a special differential equation, but has led to certain things being completely independent of t, which is kind of time. So now we want to actually try and solve this differential equation in the case where n is t0t and m is capital A, B, C, D at time 0. Find m as a function of t. Okay. So I feel like I want to use these results to set up some differential equations. So this is going to mean, these results are going to mean that a plus d is some constant, and I'll call it k. It says that the trace of the trace of m squared, so a squared plus 2bc plus d squared, is some other constant, and what was the last one? The determinant, ad minus bc, is some final constant. Well, I could try and work out these constants at time 0. So when t is 0, t equals 0, implies that this k will be a plus d, which isn't really an exciting thing to write down, because all I'm doing is making each of the letters capital instead. But it does mean that we theoretically know each of those constants. So if I had an expression for a, then k is simply if I had an expression for a, then d would be k minus that a expression. So probably I only need to solve for maybe 1 or 2 of these variables. I didn't want to expand out the mn minus mm side, but I feel like I probably have to. But m is all functions of t. So this is going to be really unpleasant. Anyway, let's do it. dm by dt is m times n. So that's going to be a. I'm going to write it out properly. I've got deep enough into the question where I'm going to have made a mistake somewhere. And I don't think I've made one yet. So I'm going to be a little more cautious with my matrix multiplications now. So this is going to be AT Okay, that's interesting. Lots of things are going to cancel, actually. I've looked ahead at the other multiplication, and some things are going to be, maybe not. And then finally ct plus dt minus, this is going to be at plus ct, bt plus dt, just ct, and finally just dt. And we can say that this is actually b dash c dash a dash b dash c dash d dash. So we have four simultaneous differential equations. We've got a dash is negative ct, b dash, if I subtract them, will be at minus dt, c dash. C dash is a pleasant one because that's the one that comes out to be 0. So the c component is constant. D dash, if we finish that off, is just ct. So what does all this mean? So c dash, or c itself, is just a constant. I'm starting to run out of constants, so I'll call it n. Don't like to use n really, it implies it's a whole number, which it not necessarily is. And then a, I'm going to definitely run out of letters. I'm not going to enjoy. I think I'm going to go into Greek here. So alpha, beta, gamma, delta. So I'm going to say C is going to be delta. So then A dash is negative delta T. Increase the power divided by the new power when we undo that derivative. So it's going to be a negative a half delta squared, delta T squared plus an unknown constant. The D I could also solve in exactly the same way, half delta T squared plus, sorry, I've got a gamma and a delta. I want this one to be gamma and then delta for the D. And if I do briefly check back, if I add the A and the D together, yes, the T's have all cancelled out. So that constant nature has worked out perfectly. And then finally, the B dash is going to be a bit more complicated. So B dash is equal to A minus D times T. So if I do A minus D, that's going to be negative delta T squared. But I'm timesing by another T plus alpha minus delta T. So an expression for B is going to be the most complicated. It's negative a quarter gamma T to the 4. It's alpha minus delta T squared. I need a half in front plus some unknown constant. And now we can try and find, hopefully find each of these unknowns. So when t equals 0, we're going to have that this delta thing is the capital C. That's completely independent of time already. Using the A expression, oh, when t is 0, then just alpha equals A, and oh, it's actually just going to turn out that each of these is quite dull. So therefore, the matrix M as a function of t is going to be M equals, so the A term is going to be negative a half ct squared plus A. The C term, I'm going to do that because it's easy. The B term's the most unpleasant, negative a quarter ct4 plus A minus D T squared plus B. And finally, the D term is a half CT squared plus D. And if I do add the trace there, the trace works out. I don't really want to go back and check all of these conditions. It might be worth doing if I had time at the end, but I don't really want to multiply those two together and subtract off those multiplied together and hope all the t-ness cancels. Actually, just looking at it, if you do imagine expanding those out, you can see the cancellation happening with all the t terms quite nicely. So yeah, the determinant condition holds. May not want to do the trace of m squared though. Okay, part 4. In this part of the question, we now have a different differential equation that we're trying to solve, which doesn't have the subtract in it. So we only have the mn, where the entries in the matrix n are again functions of t. The trace of m is non-zero and independent of t. Is it necessarily true that the trace of n equals 0? Interesting. So we're not trying to solve anything here. We're just asking, m is nice, trace is non-zero. Is it true that the trace of n is non-zero? And I'm actually going straight up to this up here, because I can get n equals quite easily. However, oh no, I am allowed. I did just want to check that the whole question, m is non-singular, the whole question I'm allowed to rearrange. So this means that I can say the trace of n is equal to the trace of m inverse dm by dt. Don't know why this is useful yet. And that is equal to 1 over det m times the derivative of det m. Okay, why was that useful? If I could somehow show that this is equal to 0, then I'll be happy. I can say, yes, trace of n is equal to 0. Well, det m itself cannot be 0, and certainly the fraction cannot be 0. So it comes down to thinking about the determinant of m. How does the determinant of m behave? Now I want to look back on how I proved earlier that the determinant of n, and I actually used, unfortunately, I used the result that I kind of wanted not to have used. So the whole proof here was based on the fact of this part I, and I've already used that. So if I use it again, I'm just going to go circular in my arguments. So how else could I proceed with this? Well, taking the trace of the determinant is just a dash d. So alternatively, I can think that the trace of m dt by dm by dt is a dash plus d dash is equal to the trace of mn. But there's no way to split the m and the n in that setup. And particularly it depends on more than just the trace, the diagonal elements of both the m and n separately. Really, yeah, so I'm still going back to this point. I'd quite like to show the determinant of m is independent of t. If we can show the determinant of m is independent of t, the derivative is 0, we're all happy. Now the determinant of m is not something particularly pleasant. This is now on my scrap paper scribbles. I'm now just trying to see anything that could help me into this problem. I have differentiated this m, det m before. I have, it's here. Now that thing doesn't look like the trace of m at all. We do know the trace of m is non-zero, and I haven't really used that fact anywhere. The fact that the trace is non-zero means I can divide by it, but I haven't got trace of m times something anywhere. So I could try something like that. But this part is stumping me slightly. We also haven't used, in the previous question, we didn't actually end up using this. Which does now feel a bit odd that we managed to solve the next part without. And you saw that my exam technique considered those first before just smacking my head into the problem itself. I could write out mn as a product. That would be the same as what I've done here. And I could put that thing equal to a dash b dash c dash d dash and get 4 simultaneous equations, but the a, b, c, d, e, f, g, and h are all functions of time, of t. And that doesn't seem useful. Alternatively, so far everything I've thought is to try and prove it is equal to 0. But what happens, and this is again exam technique, why was the question worded, is it necessarily true? And that seems to imply that it's not just a show that the trace of n equals 0. It's a, it might be, but it might not be. So I'm going to actually try and find some n's and solve for the m's. So if, now they have to be non-singular is the issue. So what if n was just the identity matrix? That's definitely non-singular. Then dm by dt is equal to m, which really is just an equation in each of its coefficients. So the a dash would equal a, which is an e to the power t style thing. So m would be a e to the t, b e to the t, c e to the t, d e to the t, which can certainly be non-singular, and the trace of m can be non-zero. So provided det of a, b, c, d is non-zero and a is not negative d, then this is an example where the trace of n is non-zero. M satisfies the differential equation. Entries are again functions of t. In this case, there is no function of t here. It's the constant function of time. The trace of m is non-zero, independent. Is independent of t. Okay, the trace of m has to be independent of t, which this example did not have. The trace of m is independent of t. So that's telling us the a a dash plus d dash is indeed 0. So I kind of want some of my other working back. I don't think I've fully acknowledged what that phrase meant. So this is not an example because the trace of m is not independent of time. So unfortunately, I might need to go back to some of the thoughts I had previously. Those thoughts using the fact that trace, I'm going to write this down again. The trace of n is equal to 1 over det m derivative of det m. But I'm also going to write that the derivative of the trace of m is 0. Okay. What does that mean? So I could put that into components. That does mean that a dash plus d dash equals 0. If I want to take the trace, again, I don't want to take the trace of this because that's just really unpleasant. I could now differentiate m, determinant of m. So this is 1 over det m times by, and I've already differentiated that once, which is that combo there. So that's the AD, that's the A dash plus AD dash minus B dash minus BC dash. But we know that A dash equals negative D dash, so we can replace that term with negative D dash A, nope, negative D dash D. Was that something I've seen before? Yes. That looks like this. Okay, something might be formulating here. So I can make that into that. I can make this one go the other way as an A dash minus 1 over det m. But that expression there was exactly, well, it's going to be negative a half of the derivative of the trace of m squared equals negative a half trace of m squared, the derivative of d by dt, the trace of m. How is that going to be useful? I've still got this 1 over det m actually. This is negative 1 over 2 det m. So now we've converted the question into trace of n is going to be equal to 0 if the trace of m squared is independent of time. The trace of m was equal to 0, but what about m squared? Now the trace of m squared is this thing here. Now BC we can write in terms of, no, it's non-zero. I was going to say if the term was 0, we can say that AD is equal to BC, but it's not. Do we know anything about the determinant of M? No, that's one of the things that we would quite like to be able to deal with. Is it necessarily true? We've still not... Well, we have used the fact that the trace is independent of t. Not used the fact that it's non-zero. We haven't divided by trace at any point yet. This is becoming a little bit more difficult. How can we link these things in the correct way? Because I really don't want to write out a lot of these expressions, because that's just going to make it so much worse. And I'm flip-flopping again between, am I trying to prove that the trace was equal to 0, or am I trying to show there's a counterexample? There's somewhere with the trace not being equal to 0. Trace being independent. Okay, I almost got an example before where I had m being something with exponentials, but that didn't have a trace that was 0. So maybe we force it to have a trace of 0 by just sneaking some things around a bit. So let's just say e to the t, and then to make the trace independent, I need a minus e to the t. So if I had something a bit more like that, and actually it doesn't even matter what these things are, they're any functions. So I'll call that b of t, c of t. And then m dash is just e of c negative b dashed of t, c dashed of t. Now, can I factorize this as something times a matrix n? Can this be written as so? And then maybe does that trace tell us something? Probably the best is to find the inverse function. And, well, actually, all I need to do is pick this. So let's say this is n. Because now n is equal to m inverse. It's n is equal to m inverse dm by dt. So the trace, now I'm going back to using that result that I've got above. The trace of n is equal to 1 over det m d by dt of det m, but now I've got a bit more concrete m. I'm kind of poking around in the dark a little bit here, but now I have what det m is, d by dt, and I might have to choose what these functions b and c are. This is going to be e to the t minus e to the 2t minus btct. And I want this to differentiate to 0. So what happens if I just pick the bt and ct to cancel this perfectly? Well, this could be, if I pick b to the t to be e and c to the t to be 1 minus e, but that's going to give me a determinant of 0. I don't want a determinant of 0, I want a determinant which differentiates to 0. So I want this subtraction to leave behind a constant. So I want b to the t ct to be equal to this plus k. Well, then I can do a similar thing. I can say this is 1 minus e to the t plus e to the minus t. So then, I've lost the k. There's the k. So then, yeah, that all works out, doesn't it? Okay, so how am I going to say all this with the scribbles that I've got here already? Pick b to the t to be equal to e to the power of t, and ct to be 1 minus e to the t plus e to the minus t. I have purposely dropped the k this time. Then the trace of n is 1 over det m. I should really check that det m is non-zero, but it's going to be it's going to be 1 by the way we've set this up. So then that expression here is going to simplify massively. We've got the right things. This is just going to be equal to -1. But this isn't what I wanted. I didn't want the trace of n to be 0. So let's pick c to be slightly different. Let's say plus t e to the minus t, so that this thing here becomes just t, well really minus t, which does not equal 0. So is it necessarily true that the trace of n is equal to 0? No. It could be this setup. And the final thing to check is, well, det m is non-zero. The trace of n, the trace of m is also non-zero. That's what I should say. With trace of m equals 1 is non-zero and independent of t, but I've managed to set this up to find an n which has a non-zero, so not necessary to have trace of n equals 0. A bit of a rough finish to that question. Again, probably could have trusted exam technique in the way the question was worded. Is it necessarily true? It's worth saying briefly why I went to exponentials. This equation looks very much like dy by dx equals a multiple of x in just normal numbers, in normal algebra, and that does have the solution x is e to the k, or y equals, I've swapped all my letters around here, y equals e to the kx with some constant. So that's why that kind of gave vibes of exponentials, and then just forcing them to work in the way that you wanted ended up finding that counterexample to the necessary condition. Hopefully that was helpful and gave you some more insights into these kind of problems. The rest of the playlist will be down below with the rest of the questions for this paper. Good luck.